All right, we are going to be looking at the June 2004 end of year exam for year 10. We're going to go through the whole paper just so you can kind of get an idea of the thought process that goes into when I take the test. So hopefully this will help with your revision. We'll start with question 1. This question is about atoms and molecules. Complete the table to show the relative masses of the particles in atoms. This is just something that you need to have memorized. So you should know that the relative mass of a proton is 1, just like a neutron. Now the mass of an electron, you could write 1 over 1840, okay, or 1 over 1800, 1 over 2000 typically will be okay. Or you could say that it's negligible because the mass is so small it doesn't really affect the total mass. But an important thing is that you cannot say 0. It does have a mass, okay? It just doesn't have a very large mass, so we say that mass is negligible, but you cannot say 0. You can say 1 over 1840 or negligible. So again, that's something you just need to learn. Now we have a diagram that shows an oxygen atom. Use the correct number to complete each sentence. It says the atomic number of oxygen atom is shown above is. So we see that our protons are black circles, and we just count 1, 2, 3, 4, 5, 6, 7, 8. That also matches the atomic number from the periodic table. It says the mass number of the oxygen atom is shown above. So we know that the mass number is the number of protons and neutrons, since they both have a mass of 1. So we just need to count up the number of neutrons as well. So we have 1, 2, 3, 4, 5, 6, 7, 8 neutrons. 8 protons plus 8 neutrons gives us a mass number of 16. In CI, draw a ring around the correct answer to complete the sentence. Oxygen atoms with different numbers of neutrons are called isotopes. Isotopes are atoms of the same element with the same number of protons but different numbers of neutrons. So they're all oxygen atoms, they've got different neutrons, that makes them an isotope. When we have our symbols down here, we represent mass number on the top and atomic number on the bottom. So an oxygen atom with a different number of neutrons has 10 neutrons. So we know we still have 8 protons because the number of protons is always the same. But now we have 10 neutrons. So we have a mass number of 18. So we know it's going to be one of these two. And we have a proton number of 8. So it's that one. Part D. A water molecule contains hydrogen and oxygen atoms. Use the correct answer to complete the sentence. Water is, well, we know it's not an element because it has hydrogen and oxygen. We know it's not a mixture because they're chemically combined. So water is a compound. 2 or more chemical elements chemically combined or chemically bonded together. If we were to draw a ring around the structure, we have the hydrogen with the oxygens in the middle. The oxygen is bonded to both hydrogens. This, for the type of bonding in a water molecule, this is a covalent bond, okay, because the electrons are shared. Remember, ionic bonds have to have a metal and a nonmetal. Metallic bonds obviously have to have a metal. We don't have a metal, so we know that it's going to be covalent. Draw a ring around the correct answer to complete each sentence. The bonds in a water molecule are formed by gaining, losing, sharing electrons. Since we're not forming ions, we're not gaining or losing electrons, we're sharing those electrons in our covalent bond. Draw a dot and cross diagram to represent the bonding in water. Show the outer electrons only. Now, it's important when we think about dot and cross diagrams, we need to ask ourselves, is this an ionic bond or is this a covalent bond? Because the way that we draw the structures are a bit different. We already set up here that water was a covalent bond, so we show sharing of electrons in that Venn diagram-like structure to show that they're sharing things, that they've got them in common. So we know our oxygen goes in the middle. And we know we have an overlap so that we can share those electrons with our 2 hydrogens. Okay? Using our periodic table, we can figure out the number of outer electrons. Hydrogen has 1, so each hydrogen has 1 electron it can share. Oxygen has 6. All right? Now each hydrogen needs a total of 2 for its first shell to be full, and oxygen and every other element needs a total of 8 for its outer shell to be full. So hydrogen only needs to share 1 electron from each oxygen. Now our hydrogen's full, it's got its 2. We still have 4 more electrons from oxygen that we need to draw in, which aren't participating in any bond, so they go here. Now just to double check, we say, does everything have the number of electrons it needs? Both hydrogens have 2, and oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So we are all set with that. Question 2. Most cans for food and drinks are made from aluminium. Aluminium is extracted by the electrolysis of molten aluminium oxide, and we've got a picture of our diagram here. There's a lot of really useful information that we can see here that can help us answer the questions later on. So it's important to reference that diagram. They gave us that information for a reason. So question A says, aluminium cannot be produced by reacting aluminium oxide with carbon. Why does aluminium oxide not react with carbon? So anytime that we have an element and a compound, okay, that's going to be a displacement reaction where we're seeing, is carbon powerful enough to displace aluminium, to kick it out of that compound, so we'd end up with carbon dioxide and aluminium by itself. So we need to say, is carbon more powerful, or our chemistry word for that is more reactive than aluminium. So we know that carbon is not more reactive than aluminium, and that's why we have to use electrolysis to extract aluminium. So if we look at our options, aluminium is less reactive than carbon. Well, that means carbon would be able to displace it. Carbon is less reactive than aluminium. That sounds pretty good. Oxygen is more reactive than carbon. Oxygen doesn't really have anything to do with it. So we're looking at carbon is less reactive than aluminium. B, cryolite is mixed with the electrolyte molten aluminium oxide. Explain why cryolite is added to the molten electrolyte. There are two reasons you could say, but you only need one since it's only worth one mark. So you could either say, okay, it's used as a solvent to dissolve the Al2O3. Okay. Remember, for our electrolyte to conduct electricity, it either needs to be molten or it needs to be in solution. The problem is that aluminium oxide has such a high melting point, it would be really, really hot if we had to melt it. So instead, we dissolve it in the cryolite. And the other benefit of this is that it lowers the melting point. These are two things that it's quite common to have a question about. So make sure that you just learn all of this information about aluminium. Uses a solvent, lowers the melting point. Suggest why the aluminium produced in the electrolysis cell is liquid. So if we look back up at our cell, okay, we can see here that our cell is at 950 degrees Celsius, so that's pretty hot. If it's at if we have a liquid, then we would know that we must that aluminium must melt at a lower temperature than 950 degrees Celsius. So our answer would be that the melting point of aluminium is lower than 950 degrees Celsius. So therefore, when it's produced in the cell, it will already be a liquid because it would have melted at that temperature. D, in this electrolyte, aluminium and oxygen gas are produced from the aluminium oxide. Use the information in the diagram on the previous page to suggest why most of the waste gas is carbon dioxide and not oxygen. You may find it helpful to write out an equation to illustrate your answer. So if we look back at our diagram like it tells us to, okay, we know that our oxygen is being produced. Since our oxygen ions have their negative charges, we know that they're going to be produced at the positive electrode. So they'll be produced at that positive anode. And that's important. We want to reference that in our answer. Okay? So we have a positive carbon anode and we have oxygen ions that are being produced. So we know that if carbon and oxygen react, they will form carbon dioxide. And that's what they want us to look at. So we know that the oxygen produced reacts with the carbon anode to form carbon dioxide. And we could even write our equation that the carbon reacts with the oxygen to form carbon dioxide. But it's important that we reference that it's taking place at the anode. Okay? And that will give us our 2 marks. 1 for knowing that the reaction is taking place and 1 for knowing that it's happening at the anode. This is one of the added problems with the electrolysis of aluminium. It adds the cost to the cost because we have to replace those carbon anodes because they get worn away as they react with that oxygen. So that's another cost in this process. E, the extraction of aluminium is an expensive process. Give one reason why aluminium is such an expensive metal to extract. So aluminium is one of the most common metals on Earth. there's a huge amount of it, but it's pretty expensive to extract, and the reason for that is because we have to use electrolysis. To use electrolysis, we need electricity, and it costs a lot of money to produce electricity. So the reason why the extraction of aluminium is so expensive is because the electricity that's needed for the electrolysis is very expensive. And on this one, you need to make sure that you're mentioning that we need electricity and that it has to use electrolysis. Those are the two important parts for that mark. Part F, some statements about aluminium are given below. Tick 2 statements that are the correct reasons why aluminium is used to make cans. That's important, okay? Aluminium conducts electricity, that's true. Aluminium is a light metal. Aluminium has a low density. Aluminium is resistant to corrosion. Now, light and density, a lot of times we confuse these two things, and we say light when we really mean low density. So you could have a piece of aluminium that weighs 2,000 tons, or you could have a piece of aluminium that weighs 1 gram. So how light it is completely depends on the size of the piece. So that's not a property that we're looking at. The other 3 are all properties of aluminium, but only 2 of them tell us why we use it to make cans. So we don't really use cans to conduct electricity. That one doesn't really make sense. Having a low density, well, that would be a good thing because then your average size can wouldn't be too heavy. So that's going to be one. And it's resistant to corrosion. Well, that means it's not going to react with whatever is in the can, whatever food is in there, and it won't react with it. So that's going to be our second reason. Question 3. This question is all about the chemistry of the halogens and their compounds. The graph shows the boiling points of the halogens. Use the graph to help you answer these questions. Use the correct answer from the box to complete the sentence. At room temperature, chlorine is a gas, liquid, solid. So if we find chlorine on our graph, it's here. Room temperature is on there, okay? The boiling point of chlorine is less than room temperature. So at room temperature, it would have boiled, meaning it would be in the form of a gas. So at room temperature, chlorine is a gas. That's also something that you probably should know because that's kind of a fact that we've learned this year. Describe the trend in boiling points from fluorine to iodine. So as we move from fluorine to iodine, we see that those boiling points increase. Okay. The elements in group 7 all react in the same way. However, as you go down group 7 from fluorine to iodine, the elements become less reactive. Explain why all the elements in group 7 react in the same way in terms of the electronic structures of the elements. You see the word electronic structures is in bold. That means that is very important. We need to make sure we talk about electrons and how they're arranged, okay? And we want to be really specific. They're in group 7 because they all have 7 electrons in their outer shell. It's important that you use the number 7, not the same number of electrons. It didn't ask why they react the same. It asked why they're all in group 7, because they all have 7 electrons in their outer shell. So 7 electrons outer shell are the important keywords for this mark. Explain why all the elements in group 7 become less reactive as you go down the group. Now, this is something we learned about this year, okay? But it's not something that will be assessed on the exam because it's not actually in the syllabus. It's a bit of an extension. So the elements in group 7 become less reactive as you go down the group because they get larger, or their atomic radius increases. So there are more inner electrons shielding the nucleus, which means that there is less attraction between the nucleus and an incoming electron. So that's the answer to that question, although like I said, this is something that will not be on the exam. Part C, chlorine reacts with metals to produce metal chlorides. How does a chlorine atom become a chloride ion? If we look at our periodic table, we know that chlorine is in group 7. It has 7 outer electrons. We know that it wants to get to 8, so it does that by gaining 1 electron. And again, make sure you're being specific. It gains 1 electron, not just it gains electrons. It gains 1 electron. Okay? Write a word equation for the reaction between sodium and chlorine. This is important. Word equation. If you write a perfectly balanced symbol equation, you will get no marks because you didn't follow the directions. Word equation. Sodium and chlorine are reacting, so that's given for us. Sodium plus chlorine. And if we look up here at the top of the question, it says it reacts to produce metal chlorides. Our metal is sodium, so we produce sodium chloride. Describe what you would see if silver nitrate solution was added to a solution containing a chloride ion. Hopefully we remember that silver nitrate is how we test for the presence of halide ions, and they all make a different color precipitate. So we take 2 solutions, we mix them together, we make an insoluble salt, which is our silver halide, okay? And hopefully you remember that silver chloride is white, silver bromide is cream, and silver iodide is yellow. So what we would see in this reaction is the formation of a white precipitate or a white solid, but you need to in some way show that you know that it's a solid that's being produced. So formation of a white precipitate is what we would see. Chlorine also reacts with hydrogen to produce the gas hydrogen chloride. Some hydrogen chloride is bubbled into separate samples of water and methylbenzene. A piece of blue litmus paper is dipped into each solution. And state what, so I and II are saying state what we would see in the water and in the methylbenzene. Okay, so a couple of important things to notice here. We're using blue litmus paper, and remember we use litmus paper to test if something's an acid or an alkali. So we're kind of taught, we know that we're either talking about acids or alkalis here. Okay, we're also comparing water and methylbenzene, so there must be something different about those that changes the way that it's going to react. Okay. Hopefully you remember learning that water is a polar solvent, okay, whereas methylbenzene is non-polar. So we've got partial positive and negative charges in the water that attracts it to the ions, to the electrons in the hydrogen chloride. So we've got some attraction there, and if we remember when things dissolve in water, things like hydrogen chloride, they dissociate and they break down into their ions. So if we dissociate hydrogen chloride and it breaks into its 2 ions, hydrogen and chlorine, we will get hydrogen ions. And we know that hydrogen ions are what makes something an acid, so that will affect our litmus paper. So we've got 2 marks here. We need to make sure we're giving 2 marks worth of information. So we would say when the HCl dissolves in water, it produces hydrogen ions, okay, which makes it an acid. So the litmus paper will turn red. Comparing that to methylbenzene, this is a non-polar solvent. So that means that there's no attraction between the hydrogen chloride particles and the methylbenzene, so it's not going to get pulled apart into those different ions. So no H plus will be formed, which means that the litmus paper will stay blue. Question 4. This question is all about the structure and bonding. The diagrams below represent the structures of 6 substances. So the first thing I would recommend is let's just look at this picture and hopefully see everything that we remember about them. So if we look at these different structures, there's a lot of information there that we can use. Structure A, we've got positive and negative ions. They're bonded together in a big 3D structure, so that's an ionic compound. It's probably sodium chloride based on its shape, but you just need to know that it's ionic. Okay. B, hopefully this is a structure you recognize. It's a lot of the same atoms in a giant structure. This is diamond. Here, sorry about that. Here we just have a bunch of atoms kind of floating around. So these are just atoms of some element. Okay. D, again, we have atoms bonded together in a big structure, but this time they're not all the same. So hopefully we recognize this as the structure of silicon dioxide. E, we've got molecules here because we've got more than one atom. But since both of the atoms are the same, we know that this isn't a compound, this is an element. And if we remember our elements, we've got two of them bonded together. This is a diatomic element. And the last one, F, we have a bunch of the same atoms bonded together, and we've got layers with space in between them. So hopefully we recognize this as graphite. That's the other allotrope of carbon that we should be familiar with. All right, so those are 6 structures that we need to know about for this exam. So give one substance that is made up of atoms. So we have atoms, we have ions, okay? Compound A is made up of ions, but everything else only has atoms in there. So actually, for question A, we could say B or C or D or E or F, and any of those would be the correct answer, as long as you didn't say A, because A is made up of ions, not of atoms. II says is a compound. So remember, for something to be a compound, we have to have more than one element, and they have to be bonded together. So we could look, we've got more than one element in here, more than one ion in here, bonded together, so that could work. Here, all of our atoms are the same. Here, all of our atoms are the same. Here, we've got 2 different atoms bonded together, so that's good. These are the same, and these are the same. So either A or D represents a compound. All right, and the last one has ionic bonding. In order to have ionic bonding, we have to have oppositely charged ions, and only A has oppositely charged ions. So A is the only one that could represent ionic bonding. For B, the following question asks you about the properties and bonding of substance E. Draw a ring around the correct answer to complete each sentence. Substance E is made up of atoms, ions, or molecules. Hopefully we can see it's not ions because there's no charges, but atoms or molecules. And if we look at this, since we have 2 atoms bonded together, even though it's an element, those are actually molecules. So molecules is the best answer for that. All right. How strong are the forces between the particles in substance E? So if we look back at substance E is that diatomic element, and it says how strong are the attractions between those particles. So it's not talking about inside the particles, that chemical bond, it's talking about between the different molecules. And hopefully you remember, this is clearly a gas, and anytime we have simple molecules, there's not a huge amount of attraction between those different particles. We just have those weak intermolecular forces. So we have weak attraction between the particles, okay? The next one, does substance E have a high or low melting point? Explain your answer. Well, if we only have weak forces, it doesn't take a lot of energy to overcome them. So we would have a low melting point because we have weak attractive forces. So there's not much holding them together to stop them from melting. And those forces, again, are between molecules. C, explain why substance A has a high melting point. So if we look back at substance A is our ionic compound. We've got oppositely charged ions. They're in a big structure. Those are important things to mention. Now, there's a pretty good chance that there will be a question that asks you something to do with the melting point or the structure of ionic compounds, and there are a couple of things that it's important to always say. So if it asks about the melting point, you need to say that we have strong electrostatic attraction. That strong electrostatic attraction is between oppositely charged ions. Okay. It takes a lot of energy to overcome this attraction, and that's why it has a high melting point. We have to put a lot of energy in to pulling those ions apart because they're bonded together. D, explain why substance B is very hard. Substance B is diamond, okay? We can see we just have carbon here, so we know that these are covalent bonds because we don't have a metal. But this is in a big, giant structure full of a lot of bonds, and all of those bonds are going to be pretty strong. So to try to break it or interfere with that structure at all is going to take a lot of energy, which is what makes it hard. So substance B is very hard because there are strong covalent bonds. And those bonds are between all of the atoms in the giant structure. And that means it would take a lot of energy to disrupt this structure, to break it or dent it or anything like that. E, explain why substance F is soft and slippery. If we look back at substance F is that graphite, okay? We've got strong bonds here within this layer, but look, there's not a whole lot going on between those layers. Again, we only have weak attractive forces between the layers. So it'd be pretty easy to move those layers around, and that's why it's soft and slippery. So the important things you need to say is that there are weak attractive forces between the layers. That will get you 1 mark. And this means the layers can slide over each other, which will get you the 2nd mark. Question 5 is about calcium hydroxide. Ancient artworks and monuments can be protected from acid rain if the surface is sprayed with calcium hydroxide nanoparticles. Okay, hopefully we recognize that calcium hydroxide is an alkali because it has the hydroxide in it, so it can neutralize that acid rain. Calcium hydroxide has the formula CaOH2. Draw a dot and cross diagram to represent a calcium ion. Draw all of the shells of electrons present. That's important. If you look at your periodic table, we can see that calcium has 20 protons. It has an atomic number of 20. Since it's a calcium ion, it's not going to have 20 electrons. We need to figure out how many it's going to have. So neutral calcium would have an electron structure of 2, 8, 8, 2. Okay? So when we form an ion, we're going to lose those 2 electrons. So we will form 2, 8, 8, 2 plus. So when we show our calcium ion, we're going to need 3 shells. The first one is going to have 2 electrons. The second one will have 8. And the last one will have 8. All right, that gives us a full outer shell, which is what we're looking for. And then just remember, to show an ion, we need to put it in brackets, and we need to put that charge up there. So we need the electrons for 1 mark and the charge in the brackets for a 2nd mark. Okay? We know it has a positive 2 charge. It needs to fill up the shell, so it can either lose 2 or gain 6, and it's going to be easier to lose 2, so it will lose those 2 electrons and form a +2 charge. Explain why there are 2 hydroxide ions for each calcium ion in the formula. Hopefully, if you've learned your ion charges, you should know hydroxide has a charge of -1, so that's pretty important. So that means that we need 2 hydroxides in order to have that total charge add up to 0. Remember, when we have our ionic compounds, the overall charge needs to be neutral, so we need the same number of positives and negatives. If we've got 2 positives, we need 2 negative ones. All right. A student added water to calcium oxide to make calcium hydroxide. and it gives us the equation there. Calculate the maximum mass of calcium hydroxide, which could be made from 2.00 grams of calcium oxide, and it gives us some more information. So this says 2.060 grams of calcium, and we're going to calcium hydroxide. So anytime we're going from the mass of one element to the mass of one compound to the mass of another compound, this is a reacting masses question. Okay? And the most important thing here to do is to organize yourself. So what I like to do is I like to pull all the important information from the problem. So it tells me I have 2.00 grams of calcium oxide. So I like to write that underneath my balance equation so I know which of my compounds it goes with. And it says calculate the mass of calcium hydroxide. So I'm looking for how many grams of calcium hydroxide will be produced. And now I don't have to look back at that question at all. I just know I'm going from here to here. Now to go from one compound to another, we have to be in moles because we can't compare the grams of two different substances. So in a reacting masses calculation, our first step is always to get into moles. Okay? We have a mass, we're trying to go to moles. In order to do that, moles is equal to the mass divided by the MR. So the first thing we need to find is the MR of CaO. So to find that, we just add up the ARs. So the AR of calcium is 40. The AR of oxygen is 16. So the MR of calcium oxide will be 56. Okay? So then moles equals mass over MR. Our moles is going to be equal to 2.00 grams divided by our MR, which is 56. So we will get 0.03571 moles of calcium oxide. Okay, so that's our first step. Notice here that it says you must show all of your workings. If you don't show any works, even with the correct answer, you'll only get 2 marks. So that's our first step, get it to moles. Okay, once we're into moles of calcium oxide, we can compare calcium oxide to calcium hydroxide. So step 2 is to use our mole ratio, which we get from our coefficients in the balanced equation. So we can see up here that 1 mole of calcium oxide will produce 1 mole of calcium hydroxide. So we have a 1-to-1 mole ratio. That means 0.03571 moles of calcium oxide will make 0.03571 moles of calcium hydroxide. So now we're into moles of calcium hydroxide. The last step is to convert to the units that they asked us for. So we need to step 3, unmole. Okay? We're doing the opposite of what we did here. So we're trying to find the mass. The mass is equal to moles times the MR. So now we need to find the MR of CaOH2. And it's important to remember that that 2 goes with both the oxygen and the hydrogen. So we need the AR of calcium, which is 40. We need 2 oxygens, so that's 16 plus 16, that's 32. And we need 2 hydrogens, so that's 2 times 1, so that gives us 2 more. So our MR of calcium hydroxide is 74. Okay, so to find it, we take our moles, 0.03571 moles. We multiply that by 74, our MR, and we get a final answer of 2.64 grams. Question 6. The iron produced from iron ore in a blast furnace is called cast iron. So we're talking about the blast furnace. This is hopefully a topic you revised. There is a really good chance that there will be a question on the blast furnace on the exam. It's a pretty common thing to have come up. Cast iron is converted into steel in a furnace, and we've got a diagram here to kind of show us that. So we'll come back to that when we need it for a question. Iron ore contains iron oxide. Coke contains carbon. Iron ore is first taken from the ground by quarrying. Draw a ring around the correct answer to complete the sentence. Ores contain enough metal to make extraction of the metal. This is just the definition of an ore. Okay? Ores contain enough metal to make the extraction of the metal economical. Okay? So you can have a rock that has some copper in it, but if there's not enough copper for it to be worth the money to extract it, we're not going to put the energy and the money into extracting it. So it has to be economical. B. Many chemical reactions take place in a blast furnace. Use the flow diagram at the start of the question to help you answer this question. Suggest how the blast furnace is heated. So we can see at this step here, our blast furnace is already pretty hot. It's been heated. So one of our 2 arrows coming in is going to be the way that it's heated. The iron ore is just coming in from a quarry. That's not really doing anything. So it's going to be this other arrow, this coke and air, that's going to be heating it. So it's going to be heated by the combustion of coke, where carbon reacts with oxygen in the air to form carbon dioxide. This is an exothermic reaction, so it gives off a lot of heat, and that's what heats up our blast furnace. A chemical reaction for the extraction of iron is given here. Complete the word equation for this chemical reaction. We have Fe2O3. Now, iron is one of our transition metals, and it's important to remember that transition metals can have more than one charge. So we need to say what the charge is in the name. So we need to put that in Roman numerals in the middle of the name. And we can figure out the charge of iron by looking at the charge of oxygen. Okay, so we know an oxide ion is always going to have a 2- charge. So if we have 3 oxygens, we have a total of -6. We know the total charge has to add up to 0, so this has to have a charge of +6. Okay, total +6 divided over 2 irons, that means each iron must have a 3+ charge. So we need to name this as iron 3 oxide. And remember, in an ionic compound, the ending always ends in IDE. So iron 3 oxide reacts with our carbon monoxide, it forms iron, and hopefully everybody recognizes that CO2 is carbon dioxide. Name the type of chemical reaction used in extracting iron from its ore. So here we have iron oxide, and we're going to iron. That means iron is losing oxygen, and when something loses oxygen, that is an example of reduction. Okay? You could also say redox, because we always have oxidation and reduction together. Carbon is being oxidized. But you can't just say oxidation, because carbon is what's being oxidized. So iron is taking place in the reduction. So either of those answers would get you the mark. Cast iron contains about 4% carbon. It is converted into low carbon steels. Suggest how oxygen removes most of the carbon. So it's going to remove that carbon by reacting with it, okay? And when oxygen reacts with carbon, we're going to form carbon dioxide. So the oxygen reacts with carbon to form carbon dioxide. And we can write a formula for that to show carbon plus oxygen will give us CO2. That's how the carbon is being removed out of the steel. Recycling steel uses less energy than producing steel from iron ore. Tick one advantage and one disadvantage of recycling steel. So we're looking for one good thing and one bad thing. Okay? So iron is the second most common metal in the Earth's crust. That doesn't really help us with recycling the steel because we're saying we're not getting any of the iron out. Okay? So that's kind of more related to getting the iron ore, not so much from recycling the steel. Less carbon dioxide is produced. Okay, so we produce carbon dioxide, as we've seen above, when we make steel. So if we're not making new steel, we won't be making as much carbon dioxide. That's definitely an option. More iron ore needs to be mined. Well, if we're recycling the steel, we don't need new iron ore, so that's not going to be one. And there are different types of steel which must be sorted. So if we have to sort the different types of steel, if we're going to recycle them, that's going to take time, that's going to take people to do that sorting, which is going to cost money. So the first and the second and the fourth ones are going to be the ones that we're interested in. Less carbon dioxide produced, that's definitely an advantage. Having to spend more money to sort the steel, that's going to be a disadvantage. Iron and steel have many uses, but one problem is that iron and steel both rust. Apart from oxygen, while their chemical is needed to cause iron to rust, if you think about it, if you've ever left a bike outside that maybe has some of the paint chipped away or something like that, and it rains, it's much more likely for it to rust. And that's because we need oxygen. We also need water for rust to form. Salt will speed up the process, but salt doesn't have to be there. Water and oxygen have to be there. Suggest a possible way of preventing the iron hull of a ship from rusting. Explain briefly how this method of rust prevention works. So on the hulls of ships, we use sacrificial anodes. Okay. And this is, again, something that you kind of just need to learn. So with a sacrificial anode, we attach a more reactive block of metal So it has to be more reactive than iron, so it could be zinc, or it could be aluminium, or it could be magnesium. Any of those will work. So we attach a more reactive block of metal to the bottom of the ship, and that means that this more reactive metal is the thing that's oxidized instead of the iron, okay? So the more reactive metal is oxidized instead of the iron, or it reacts with the water and oxygen instead of the iron. Don't say it rusts instead of the iron because it doesn't rust, only iron rusts, okay? So that's how sacrificial anodes work. Question 7. Carbon dioxide is a colorless, odorless gas. It is one of the gases found in the exhaust gases from a car. Describe a chemical test to prove that carbon dioxide is present in the exhaust gases of cars. We've seen this quite a few times now, but it's just a test you need to know about. We test it with lime water, and the lime water will go milky or cloudy white. So that's how we test for the presence of carbon dioxide. In the combustion engine of a car, petrol vapor burns with oxygen gas, releasing lots of energy, and the waste gas is carbon dioxide and water vapor. The equation for the reaction is given below. In a typical 3-mile car journey across London, the car will use up 90 decimeters cubed of petrol vapor. Calculate the volume of carbon dioxide that would be released into the atmosphere over this journey. So we've got information about one gas we're starting with, information about a second one. This is a reacting gases problem. So it's very similar to reacting masses, but this time we're working with gases instead. So again, I like to sort myself out. I say I have 90 decimeters cubed of petrol vapor, so I put that underneath my petrol vapor. And it's asking me the volume of carbon dioxide. So I want to know how many decimeters cubed of carbon dioxide I can produce. So just like with a reacting masses problem, the first thing we need to do to compare two different things is get it into moles. So step 1 is to mole. But this time, because we have gases, we don't need the MR. We need to use that one mole of gas has a volume of 24 decimeters cubed. So moles is equal to the volume of the gas at room temperature and pressure divided by 24. So we're going to take our 90 decimeters cubed and divide it by 24, and we'll get 3.75 moles of our petrol, our CaH18. So that's step 1. Step 2 is to use our mole ratio. So we need to get from moles of petrol to moles of carbon dioxide, and we get that from our coefficients in our balanced equation. So we can see for every 1 mole of petrol we burn, we produce 8 moles of carbon dioxide. We're making 8 times as much. So since we're making 8 times as much, we need to multiply the moles by 8. So we take our 3.75 moles, we multiply it by 8, and we get 30 moles of CO2 being produced. Okay? The last step is to get it into the units that it asked for, so we need to unmole. We have moles, we want to get to volume. Volume is equal to the moles times 24. So we take our 30 moles of CO2, we multiply by 24, and we get a total volume of 720 decimeters cubed of carbon dioxide formed. Suggest one environmental problem associated with the release of carbon dioxide into the atmosphere. I'm pretty sure, hopefully everybody should know that carbon dioxide is a greenhouse gas. So that's an acceptable answer. You could say global warming is a problem. Okay, so it's a greenhouse gas that causes global warming. Suggest one industrial use of carbon dioxide. There are 2 industrial uses of carbon dioxide that Edexcel expects you to know. The first one is that it's used in fire extinguishers. This is because carbon dioxide is more dense than air, so it sinks down on top of the flames below the air, and it doesn't let the oxygen in and air get into the fire. The other one is in carbonated or fizzy drinks. This is because carbon dioxide is slightly soluble in water, so we can dissolve it in water we can dissolve it in the water in the fizzy drinks under pressure, and then when we open that lid, it slowly comes out of the solution. So we get some bubbles, and those bubbles last for a little while. All right. In the laboratory, carbon dioxide is also released when sodium hydrogen carbonate decomposes on heating. In this process, chemical Z and water are also released. Chemical Z was found to contain 1.38 grams of sodium, 0.36 grams of carbon, and 1.44 grams of oxygen. Calculate the empirical formula of compound Z. So, and again, we must show all of our working. Empirical formula, remember, is the simplest whole number mole ratio. So we need to get into moles, and then we need to find that ratio. And the most important thing with an empirical formula problem is to stay organized, because there's going to be a lot of numbers. You need to remember what goes with what. So I like to organize myself like so. I've got my three elements, and the first thing I know about them is their masses. So I have 1.38 grams of sodium, 0.36 grams of carbon, and 1.44 grams of oxygen. Okay, I need to get it into moles. Hopefully remember that moles is equal to mass over AR for elements. We have our ARs here, so we need to do 1.38 divided by 23, 0.36 divided by 12, and 1.44 divided by 16. And if we do that, we get 0.06 moles of sodium, 0.03 moles of carbon, and 0.09 moles of oxygen. Okay, now we can't write a chemical formula, Na 0.06, C 0.03, O is 0.09, so we need to get whole number ratios. And the way that we do that, and this is the step that everybody forgets, is we need to divide by the smallest number to get the ratio. So since 0.03 is our smallest number of moles, we're going to divide them all by 0.03. And this will give us our ratio. If we do this, we get 2 to 1 to 3. Now, if you get something like 1.987, that's close enough that you can round it to 2. If you get something like 2.5, that's a bit far off. So you need to think about what whole number could I multiply everything by to sort that ratio out. So if you get a 0.5, you need to double everything. Okay, but here we get nice even numbers. So the last step is to write it as a formula. We have 2 NAs, so that's Na2. We have 1 carbon, so that's C, and we have 3 oxygen, so that's O3, and that gives us sodium carbonate. Question 8 is actually about the Haber process, which used to be taught in year 10, but has now been moved to year 11. So you have not learned about this yet. It will not be on your test. The whole first part of question 8 we can't even do, okay? And all of this stuff is stuff we wouldn't be asked about. But there are F and G are things that we could answer. So a solution of ammonia in water is alkaline. Which one of these values could be the pH of a solution of ammonia? Alkaline things will have a pH above 7, so that's 10. We can also do the percentage yield. Okay, you must show all your good working. So it says ammonium sulfate can be made by reacting ammonia solution formed in the Haber process with sulfuric acid. In a reaction, the manufacturer has calculated that the process can produce 7 tons. So ideally, if everything went absolutely perfect, we would make 7 tons. But we only actually made 2.5 tons. We want the percentage yield. So percentage yield, we just take the part we're interested in, divided by the total, times 100, just like any percent. So percent yield is equal to our experimental mass, the mass we actually got in the experiment, over our theoretical yield, which is how much we should have made. So we take and then we multiply by 100 to get percent. 2.5 tons. So 2.5 tons divided by 7 tons times 100, and we get 35.7% yield. Question 9. The electrolysis of sodium chloride solution is an industrial process. The diagram shows the apparatus used in a school experiment. Okay? One of the products of the electrolysis of sodium chloride solution is hydrogen. Explain why hydrogen ions move to the negative electrode. We know hydrogen ions have a positive charge, and we know opposites attract. So positive hydrogen ions are attracted to the negative electrode because opposites attract. Show how hydrogen ions change into hydrogen gas by writing the balanced ionic half equation for the process occurring at the negative electrode. When we write half equations, there are a couple of important things to remember. The first thing is we're always starting with our ions. So we're starting with our hydrogen ion. Ions have charges, so write that charge, okay? We're forming hydrogen gas, which is H2. Since we need 2 hydrogens in our gas, we're going to need 2 hydrogen ions, okay? We have up 2 positive charges. We need to make it equal 0 because the charges on both sides has to be the same. So 2 positives, we need to add in 2 negatives, we need to add in our 2 electrons. So 2H plus 2 electrons will give us our hydrogen gas. Sodium chloride does not conduct electricity when solid. Explain why sodium chloride solution does conduct electricity. In a solution, those ions have been dissociated, they've been pulled apart by the water molecules. So our charged ions in a solution, the charged ions are free to move, and we need free to move ions for an ionic compound to conduct electricity. Here we have the overall symbol equation for the reaction. Balance the equation and add the missing state symbols. So we'll start with balancing and then we'll come back to the state symbols. So balancing really is just one big guess and check. We just need to go back and forth. So let's start with sodium. We've got 1 sodium, so that one's okay. We have 1 chlorine. Here we have 2 chlorines. So we need 2 chlorines over here. We need to put a 2 in front. Well, this gives us 2 sodiums, so we now need to add 2 sodiums there. Okay? We have 2 hydrogens, and on this side we have 2, 3, 4 hydrogens. So we need a 2 here to give us 4 hydrogens. That gives us 2 oxygens, and we have 2 oxygens, so we're all balanced. Then we need to add in our state symbols, okay? It has told us a bunch of times in this problem that we have sodium chloride solution. Our state symbol for solution is AQ, okay? Water is a liquid. Chlorine is produced as a gas at room temperature. Sodium hydroxide stays in solution, and hydrogen is also produced as a gas. And you should know those 3 things because you should have learned them about the electrolysis of brine. Question D, in the UK, water companies use some of this chlorine and add it to tap water. Explain why chlorine is added to tap water. This is to kill any bacteria. This is why they send chlorine tablets to countries where they have a clean water shortage, because they use those chlorine tablets to kill the bacteria so they can drink the water. Given industrial use of the sodium hydroxide manufactured in the process, in this case it's important, if you're going to say the use is to make something, you can't just say what it's making, you have to say to make that. So sodium hydroxide is used to make paper. If you just say paper, that's wrong, because sodium hydroxide is not paper. It's used to make paper. It's also used to make soap, and it's also used to make bleach. So any of those would be acceptable. Okay? Now F on here is quantitative electrolysis, so the calculations that go with electrolysis. You will have to be able to do these for the GCSE exam next year. However, they are not going to be on this year's end of year exam, so you don't need to worry about those for right now. And with that, we're done with the paper.